Have you ever held a piece of gold? Maybe, a ring on your finger or perhaps a special coin. Gold is beautiful. It shines with a warm yellow light. For thousands of years, humans have loved gold. We've used it for money, for art, and for jewelry. It is rare and precious. But have you ever stopped to wonder where it comes from? Not from a mine deep in the earth. I mean, where did it really come from? Where was it made? The answer is not on our planet. It is not even in our solar system. The story of gold is a story written across the vastness of space and time. It is a cosmic tale of incredible violence and creation. The answer lies with some of the strangest objects in the cosmos. These objects are the leftover cores of giant stars that have died. They are incredibly small, yet unbelievably heavy. They are called neutron stars. The story of your gold ring begins with the death of a star much bigger than our sun. It is a story of cosmic collisions that are more powerful than anything we can create on Earth. Let's think about the scale of the universe. It is almost too big to comprehend. There are billions of galaxies. Each galaxy contains billions of stars. Our own galaxy, the Milky Way, is just one of them. Among these countless stars, some are truly gigantic. They are many times more massive than our sun. When they run out of fuel, they do not just fade away. They go out with a bang, a really, really big bang. This explosion is called a supernova. For a long time, scientists thought that supernovae were the source of all the heavy elements. But there was a problem with this idea. When they looked closely at the numbers, they did not add up. Supernovae could explain where elements like iron came from, but they could not explain the amount of gold we see in the universe. To understand a neutron star, we first need to understand the death of a very big star. Imagine a star that is much, much larger than our sun, perhaps 10 or 20 times more massive. For millions of years, they fuse lighter elements into heavier ones in their super-hot cores. They start with hydrogen, just like our sun. They fuse it into helium, then they fuse helium into carbon, carbon into oxygen, and so on. Eventually, the star builds up a core of iron, and iron is a dead end for fusion. Without the outward push from fusion energy, the star's own immense gravity takes over. In less than a second, the iron core collapses catastrophically. The shock wave rips the star apart in a titanic explosion. We call this a supernova. For a few weeks, this single exploding star can shine brighter than its entire home galaxy. Left behind in the center of this expanding cloud of gas and dust is the collapsed core of the dead star. This is the cosmic tombstone, the remnant of a once mighty giant. Let's zoom in on that collapsing iron core. As gravity crushes it with unbelievable force, the very structure of matter begins to break down. The pressure becomes so intense that it overcomes the forces that keep atoms separate. The gravity is so strong that it forces the negatively charged electrons to merge with the positively charged protons. When an electron and a proton are squeezed together, they combine to form a new particle, a neutron. The core becomes a substance made almost entirely of neutrons, packed together as tightly as physically possible. It is like one gigantic atomic nucleus just a few kilometers across. A single teaspoon of a neutron star would weigh billions of tons here on Earth. That is how dense they are. Let's try to get our heads around just how dense a neutron star is. We have said it is like crushing our sun into a sphere the size of a city, say about 20 kilometers in diameter. Imagine you could take a teaspoon and scoop up a tiny bit of neutron star material. That single teaspoonful of neutron star stuff would have a mass of about 5 billion tons. This incredible density has profound effects on the space and time around the neutron star. According to Einstein's theory of general relativity, massive objects bend the fabric of space-time. The gravity on the surface of a neutron star is about 200 billion times stronger than the gravity on Earth. If you could drop a marshmallow onto a neutron star from a height of 1 meter, it would hit the surface with the energy of a powerful bomb. The extreme properties of neutron stars do not stop at their density. They are also born spinning incredibly fast. This is due to a principle called the conservation of angular momentum. A newborn neutron star can spin hundreds of times every second. That means a point on its equator could be moving at a significant fraction of the speed of light. On top of this, neutron stars have unbelievably powerful magnetic fields. The result is a magnetic field that can be 1,000,000,000,000 to 1,000,000,000,000 times stronger than Earth's magnetic field. Many of these spinning neutron stars act like cosmic lighthouses. Their powerful magnetic fields create beams of radiation that shoot out from their magnetic poles. As the star spins, these beams sweep across space. Our story now brings two of these incredible objects together. Imagine, in the vast emptiness of space, not one, but two neutron stars. They are partners in a cosmic ballet. Many massive stars are born in pairs, orbiting each other. So when both of these stars live their fast lives and die in spectacular supernova explosions, they can leave behind a pair of neutron stars. This dance is a long and patient one. It can last for millions or even billions of years. They might start off quite far apart, taking many hours or even days to complete a single orbit. According to Albert Einstein's theory of general relativity, these orbiting masses are constantly stirring the fabric of space-time. They are creating tiny ripples that spread outwards at the speed of light. These gravitational waves carry energy away from the binary system. As the system loses energy, the two neutron stars are drawn closer together. Their orbit begins to shrink. What started as a slow, graceful waltz is gradually turning into a more energetic and frantic tango. The cosmic whisper had finally been heard and understood. Let's listen more closely to this cosmic music. Gravitational waves are not like sound waves or light waves. They are not vibrations traveling through space. They are vibrations of space itself. Detecting such a minuscule change is one of the greatest technological achievements of our time. It requires incredibly sensitive instruments called interferometers, like the LIGO and Virgo observatories. As the two stars spiral closer together, their orbital period shortens. They swing around each other faster and faster. This causes the frequency of the gravitational waves to rise. What we detect is a characteristic signal. It starts as a low tone that rapidly gets higher in pitch and louder in volume. Scientists call this a chirp. In the last few seconds, the system is losing more energy through gravitational waves than all the stars in the visible universe are producing in light. It is a cosmic announcement, sent across millions of light years, that a gold factory is about to open for business. The final moments are a blur of extreme physics. The two neutron stars are now separated by only a few hundred kilometers. They are screaming around each other at close to the speed of light. Their immense gravitational fields are beginning to tear each other apart. The tidal forces are unimaginable. These tidal forces begin to deform the neutron stars, pulling them out of their perfect spherical shape. Material starts to be ripped from the surface of one star and pulled towards the other. A bridge of super-dense neutron matter may form between them. The magnetic fields of the two stars, each trillions of times stronger than Earth's, also begin to interact. They twist and snap, releasing colossal amounts of energy into the space between the stars. Finally, after millions of years, they crash into each other. In the very last millisecond, the final gap between the two stars is closed. The two city-sized atomic nuclei, weighing a combined total of nearly 3 times the mass of our Sun, slam into each other. The moment of impact unleashes a burst of energy and radiation so intense it is almost beyond comprehension. And in the fiery aftermath of this collision, the conditions are finally right for the universe to forge its most precious metals. Let's step back for a moment and, really appreciate what we've just witnessed. Then, in 2015, we finally learned how to hear these whispers. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first ever direct detection of gravitational waves. 2 years later, on August 17, 2017, came the moment that changed everything for our story. The LIGO and Virgo detectors picked up a new signal. It was a beautiful chirp that lasted for about 100 seconds, much longer than the black hole signals. Just 1.7 seconds after the gravitational wave chirp ended, space-based telescopes detected a short burst of high-energy gamma rays from the same patch of sky. This was the smoking gun. For the first time, we had both seen and heard the same cosmic event. It was the birth of a new era in astronomy, called multi-messenger astronomy. And in that light, we saw the unmistakable signature of gold and platinum being forged in a cosmic crash. The final whisper of the gravitational waves has faded. The two neutron stars are no longer two separate objects. They have smashed into each other at a third of the speed of light. For a fleeting instant, a new supermassive object is formed. This central remnant is a hyperdense, rapidly spinning, and incredibly unstable ball of matter. As the two stars merge, huge amounts of superdense neutron matter are flung outwards into space. This material is ejected at incredible speeds, forming a rapidly expanding cloud around the central collision point. The final act of this drama sees the merged remnant collapse into a brand new black hole, a point of infinite density from which nothing, not even light, can escape. The energy released in these few milliseconds is staggering. It's more energy than all the stars in our Milky Way galaxy will produce in 100 years. The quiet cosmic graveyard has been transformed into a blazing beacon of creation. Let's focus on that cloud of ejected neutron star matter. This cloud is expanding outwards at fantastic speeds, maybe 20 to 30% the speed of light. But this material is not stable. It's made of neutrons, which are only happy when they're packed tightly inside a neutron star. Once they're thrown out into the relative freedom of space, they begin to change. This hot, dense fireball is the perfect environment for making new elements. It's a process called the rapid neutron capture process, or the R process for short. The fledgling atomic nuclei are bombarded by a blizzard of free neutrons. In just a few seconds, the R process builds up a whole range of elements far heavier than iron, all the way to the heaviest elements in the periodic table. All of these newly created heavy elements are radioactive. Each time a nucleus decays, it releases a tiny burst of energy. The combined energy from all this radioactive decay makes the entire cloud of ejected material glow. This glowing, expanding fireball of radioactive waste is what astronomers call a kilonova. At first, it shines with a bright blue light. As the cloud expands and cools, the light becomes redder. While the Kilonova Fireball is starting to glow, something even more dramatic is happening at the very center of the explosion. Remember that newly formed black hole surrounded by a swirling disk of super-hot debris? The black hole's intense gravity and magnetic fields can grab some of the infalling material and channel it into two powerful jets. These jets are like cosmic fire hoses, blasting matter and energy outwards from the poles of the black hole. The particles within them are accelerated to such extreme energies that they produce a brilliant flash of the most energetic form of light gamma rays. If one of these jets happens to be pointed directly at Earth, we see this flash as a short gamma ray burst. For decades, astronomers had been detecting these mysterious flashes of gamma rays from deep space. The collision of two neutron stars provides the perfect explanation. It is the death scream of the merging stars. As the powerful jets slam into the surrounding gas and dust in space, they create a shockwave that continues to glow for days, weeks, or even months. By studying the gamma ray burst and its fading afterglow, scientists can piece together the story of the jet engine, the black hole that powers it, and the environment it is exploding into. So, let's put all the pieces together. The two stars merge. They form a temporary supermassive object that quickly collapses into a black hole. This cataclysm flings a huge cloud of neutron-rich material out into space. The cosmic forge has been ignited, and it is running at full power. It is in this chaotic, expanding fireball that our gold is finally made. The conditions inside the kilonova are unlike anywhere else in the modern universe. This is the key ingredient that supernovae lack. A supernova explosion is powerful, but it is a proton-rich environment. The kilonova, on the other hand, is a neutron-rich paradise for element building. It creates not just a little gold, but huge quantities of it. How much gold are we talking about? A single neutron star collision is estimated to produce many Earth masses of gold. Some estimates suggest it could be as much as 10 times the mass of the Earth in pure gold. All of this newly minted treasure is blasted out into the surrounding galaxy. The collision is not just an explosion, it is an act of cosmic seeding. So we have our cosmic fireball. It is a hot, expanding cloud of debris thrown off by the colliding neutron stars. This cloud is where the magic happens. It is a chaotic soup made mostly of neutrons, with some protons and electrons mixed in. The conditions are perfect for a special kind of nuclear reaction. Scientists call it the rapid neutron capture process. This is the universe's secret recipe for making gold. The main ingredient is a massive number of free neutrons. You start with some seed nuclei. These are simple atomic nuclei, like iron, that might have been present in the neutron star's crusts. Then you add an incredible storm of neutrons, Because there are so many neutrons, and the conditions are so extreme, the nuclei capture them very, very quickly. A nucleus will grab a neutron, then another, and another, before it has any time to think about becoming stable. Imagine trying to build a tower of bricks as fast as you can without worrying if the bricks are straight. The tower would get very tall very quickly, but it would also be very wobbly. This entire process from seed nuclei to giant unstable atoms happens in just a few seconds. In the blink of an eye, the Kilonova Fireball has cooked up a whole suite of elements from the bottom half of the periodic table. And nestled right there in the middle of this creative burst is element number 79. A nucleus with 79 protons and, after all the chaos, 118 neutrons. This is the element we call gold. The R process has finished its frantic work. The expanding cloud is now filled with a bizarre collection of super-heavy, radioactive atoms. But these are not the stable elements we know and love yet. They cannot stay this way for long. So these exotic nuclei begin a journey to become more stable. They do this through radioactive decay. This is where a neutron inside the nucleus transforms into a proton, and in the process, it spits out an electron. Each time a beta decay happens, the nucleus changes its identity. This process happens over and over again. The newly formed atoms cascade down a chain of decays, shedding neutrons for protons. This radioactive decay is what powers the kilonova's glow. Every single decay releases a tiny packet of energy. When you have tons and tons of material decaying all at once, that energy adds up. By studying the colors of the kilonova light and how they change over time, scientists can see the fingerprints of the elements being formed. In the light from the 2017 collision, they saw the clear signature of heavy elements. Finally, after several days of this decay cascade, things begin to settle down. The super-heavy, wobbly nucleus with 79 protons has shed its excess neutrons through a series of decays. It has settled into its final, comfortable, form-stable gold. The collision is over. The kilonova has faded. But the story of the gold is not finished. The explosion from the neutron star merger flings this cloud of new elements outwards into interstellar space. This precious cloud mixes with the existing gas and dust that drifts between the stars. It is like adding a swirl of gold paint to a vast cosmic canvas. This process has been happening for billions of years all across the universe. Countless pairs of neutron stars have danced their deadly dance, collided, and seeded their galaxies with heavy elements. Eventually, gravity will begin to pull parts of this cloud together. A new generation of stars and planets will begin to form from this recycled material. Our own solar system was born from such a cloud about 4.6 billion years ago. When the Earth formed from this swirling disk of cosmic leftovers, it incorporated these heavy elements. Gold, being very dense, mostly sank towards the planet's core during its molten youth. This is the gold that we find in mines today. It is a direct physical link to these ancient cataclysmic events. Every atom of gold on Earth is a tiny relic, a souvenir from a neutron star collision that happened billions of years ago in our corner of the Milky Way. It is a piece of cosmic history you can hold in your hand. The discovery that neutron star collisions are the main source of gold has solved a long-standing cosmic mystery. The observation of GW 170817 changed everything. It provided the smoking gun. We heard the gravitational wave chirp of the inspiral. We saw the flash of the gamma ray burst, and we watched the glow of the kilonova, powered by the creation of elements like gold. This discovery gives us a new way to look at the universe. It is not just a collection of stars and planets. It is a vast, interconnected ecosystem. The death of one type of star provides the building blocks for another. The universe is constantly recycling itself, transforming energy into matter, and simple matter into complex and precious elements. The early universe had no gold. Today, thanks to colliding neutron stars, it is gilded with it. Think about the sheer scale of it. A single collision can produce more gold than the entire mass of the moon. There is likely a neutron star collision happening somewhere in the universe every few minutes. Over the 13.8 billion year history of the universe, this has added up to a lot of gold. It is a cosmic treasure, scattered among the stars, waiting to be gathered up by new solar systems. This knowledge transforms our relationship with the elements around us. Gold is not just a shiny yellow metal valued for its rarity and beauty. It is a piece of the universe's most violent history. So the next time you see a piece of gold jewelry, take a moment to consider its incredible journey. It is a story of dead stars, cosmic dances, gravitational waves, and an explosion of unimaginable power. Our journey has taken us across billions of light years and through billions of years of cosmic history. We started with a simple question: where does gold come from? We found the answer not in the ground beneath our feet, but in the most extreme and violent corners of the universe. The story of gold is the story of neutron stars. It is a tale of massive stars living fast and dying young, leaving behind city-sized atomic nuclei as their corpses. It is a story of a long, slow cosmic dance, a patient spiral towards a final cataclysmic embrace. This grand narrative connects us directly to the cosmos in the most intimate way imaginable. The gold wedding ring on a finger, the delicate gold leaf on a work of art, the gold wiring inside a smartphone. All of these objects have an origin story of epic proportions. Each atom of that gold was forged in the heart of a kilonova, a fireball of creation born from the collision of two dead stars. That atom was flung across the galaxy, journeyed through the interstellar void for eons. This connection is not just poetic, it is a fundamental scientific truth. The universe is not a distant, separate stage on which we are merely spectators. We are active participants, built from the ashes of long-dead stars and the debris of cosmic collisions. The iron in our blood was forged in the core of a dying star that exploded in a supernova. The carbon that forms the basis of our bodies was created in the hearts of stars long ago, and the gold that we treasure is a direct relic of a neutron star merger. Therefore, when we look up at the night sky, we are not just looking at a collection of twinkling lights. We are looking at the grand cosmic ecosystem that created us. The universe is not just out there, it is within us. We are made of stardust, and some of that stardust, the most precious and rare, is golden. We are truly children of the cosmos, connected to its grandest events. The confirmation that neutron star mergers create gold is a triumph of modern science. It is a story of human curiosity and ingenuity. But this discovery is not the end of the story. It is a magnificent beginning. This new era of multi-messenger astronomy, where we can both see and hear the universe, promises even more incredible discoveries to come. We are just beginning to listen to the symphony of the cosmos. So let this story be an invitation to wonder. The next time you hold something made of gold, remember its violent and spectacular birth. Remember the dead stars, the gravitational dance, and the cosmic alchemy that transformed them into the precious metal in your hand. Look up at the stars and appreciate the incredible ongoing story of creation and destruction that unfolds across the cosmos every single day. The universe is a place of breathtaking beauty and power, and we have only just begun to understand its secrets. The journey of discovery continues.